Hi, everybody. Thanks for being here. And we are going to start with an overview of the key building blocks to Seaport, and then we'll dive right in on all of the new functionality that's introduced in Seaport 1.4. And feel free at any point to jump in with questions or if you want to learn more about something. We'll talk about bulk listings, the new and improved zones, contract-based listings, and some of the fun optimizations. And then we'll wrap up with a more general Q&A. All right, let's get to it. Okay. Seaport is a marketplace protocol for safely and efficiently buying and selling NFTs. It powers OpenSea as well as over 100 other marketplaces throughout the NFT ecosystem. The basic premise is that you offer some combination of tokens or items, and then in order to take those offer items, you need to receive back consideration items, you or others. So you wrap up an offer array and consideration array along with other parameters like the type of the listing into what's called an order. There are also zones which extend the native functionality of Seaport for specific order types, restricted orders. There's the conduit, which is an optional contract that will perform token transfers, so you approve the conduit to move your tokens. There are criteria-based items, which are ERC 721 and 1155 tokens, where you supply a Merkle root in place of a token ID, and then the caller specifies the identifier they want. This is used for collection and trait-based bids and offers. And there's also partial fills, so you can specify a fraction to fill if the order type allows it. And every item on that listing is scaled down by precise fraction. All right. Seaport 1.4 introduces it's an iteration. The interface is mostly unchanged. One of the big new features is called bulk listings. So this is the EIP 712 payload that you sign when you create a Seaport listing. It contains all of the top-level order components, including the offer and consideration arrays, and you can see the types for those as well. Now, for a bulk order, there are actually 24 different payload sizes. This one is for size 7, or a height of 7, which includes 128 distinct orders. And it's still an EIP 712 payload, and they all will have, it'll be a multiple of 2, up to 16 million listings in a single signature if you have a height of 24. But each leaf at the very end of this big binary tree is just the exact same structure as a single listing. So when you sign this in MetaMask, for instance, it's gonna present this whole tree. Ostensibly, you can go through and actually see everything that you're signing, in contrast to other NFT marketplaces that you just sign a opaque 32-byte hash, which could be anything. Now, it's maybe not realistic if you're signing 16 million listings at once to go through and manually review. It's good practice to cap the size of these order trees, but automated tooling and security extensions and things like that are now able to scan this whole tree for any potentially malicious payloads. The way that this operates, when you have a bulk listing, you sign for the bulk type hash, depending on the size, and you get an ECDSA signature. We convert all of the inbound ECDSA signatures to EIP 2098 compact signatures with 64 bytes. But you can also leave it at 65 bytes. This example is for 64 bytes. The way that these work is you take that ECDSA signature for the whole payload and you include a 3-byte key and a number of 32-byte words that are equal to the height of the tree that you signed. That gives you everything you need to recover a specific order hash using the proof and the original type hash. The way that this works on the contract is that you get the original digest using the order hash that you're trying to fulfill. Basically, every single bulk listing has its own bulk signature that shares the same signature, but then also has a key and a proof. So once you've generated a bulk listing with a bunch of different orders on it, you can just generate a distinct bulk signature that shares the same ECDSA sig at the beginning, but they all have a unique signature when you take it all in conjunction. And this is also really nice because from the fulfillment side, you can just treat this new longer signature as the signature, and you can forget about that it was a bulk signature to begin. Also nice on the back end because you can just store a slightly longer signature and forget about the fact that it was ever a bulk listing. So what we do is we look at the signature, we cache the original signature length, which is going to be longer in the case of bulk orders than a standard ECDSA sig. We're going to check to see if the size of that signature is a valid bulk listing. And if it is, then we utilize the proof to compute a revised digest that we can recover against. And if that fails, then it will fall back to, it'll restore the original signature and still call EIP 1271 is valid signature. To see if it's a valid bulk order size, the signature, it's basically the length has to be capped between 98 and 837, and then the signature length is you just remove the key, you go mod for the words of the proof, make sure that that's either a compact or non-compact signature. And this is all pulled from the reference contracts, which are a little more straightforward. If you guys aren't familiar, the Seaport repo has the optimized production contracts, which are written heavily in assembly, but then there's also a reference implementation that is functionally equivalent, except for places where there are a few very minor locations where you can't really even do the same thing, particularly around revert reasons and things like that, without assembly. The reference contracts have no assembly, no unchecked logic, and are explicitly written to be readable and not do any crazy optimizations. The basic gist is that you use the proof to derive an equivalent to back into the full bulk order hash that was originally signed, and then that can be recovered. If the recovery fails, then we can fall back to EIP 1271. Any questions on bulk listings? We'll proceed to zone. So originally on Seaport 1.1, zones were the zone check, which basically gives a thumbs up or thumbs down on whether or not a given listing can be fulfilled, is performed pre-execution when all of the listings are being checked for their validity, and performed a static call. It was a view function, so couldn't change state. And it also provided an abridged set of parameters. All of this is to say that zones were somewhat restricted in what they could really accomplish, and in general were limiting rather than enabling. They generally made listings just harder to fulfill. A lot of the really interesting use cases for zones, things like powering lending protocols or liquidation engines, or more advanced integrations with other protocols that need to do accounting on their end to validate that tokens were transferred or what have you. They needed the zone check to be performed post-execution after all of the transfers have occurred, and they needed to be able to update state. So now zones do just that. They perform a call after all the transfers have occurred. They pass the entire set of parameters that are relevant to the order that's been fulfilled, the restricted order. They resolve the start and end amount of the various items, this offer in consideration, so that you get the specific amount that was actually spent after accounting for the change in the amount over the life cycle of that given listing. And you can update state, so that you could even imagine zones where you mint NFTs as part of the post-execution logic or that kind of thing. One thing I want to point out here, if you look at the spent item struct, the amount parameter here that's communicated to the zone, this is actually unreliable on 1.4. We disclosed this bug a couple days ago, and effectively, you can override this parameter with the recipient on the order under very specific circumstances. But what this implies is that you should not rely on this value if you're implementing a zone. This all happens post-execution, so it doesn't affect the token transfers, but the value that Seaport reports can be incorrect. Now, this is an uncommon requirement. In general, zones that are dependent on these return values, they're almost always going to be interested in the consideration array, as that dictates what everyone's getting back, and offer items can be spent by anyone that makes those consideration items that credits them all appropriately. But this is still an important thing to watch out for if you are developing a particularly niche or advanced type of zone. And if you are, I encourage you to reach out if you have any concerns or questions. You might have noticed this get Seaport metadata on the zone. Another thing that has somewhat hampered the development of zones, beyond the technical limitations that we had just described, is that there was no clear standardization around zone implementations. If you were to create a new zone, you'd have to go around and convince everyone to start using it and supporting it and understand the interface and how it worked, or you would effectively be siloed into maybe just your marketplace knows how to use this particular zone, and that defeats a huge part of Seaport's purpose, which is to make for a cross-compatible protocol that many marketplaces can use and can all share their liquidity. So we've announced this SIPs, Seaport Improvement Proposals. And the premise here is that a zone or a contract offer, we'll get into contract-based listings in a second, implement this get Seaport metadata function and emit this Seaport compatible contract deployed event to advertise and broadcast that they are compatible with Seaport. Now, each of these zones would implement a number of SIPs, which are represented by the schema, and they return the ID of the schema as well as any metadata that's sort of schema specific. And then the schemas might have additional events or functions that you call based on the SIP. So this is a way to discover exactly what's going on and to actually interact with these zones. There's another foundational SIP called SIP6, which dictates how you compose multiple SIPs and still communicate that to the zone in a standardized fashion. The key building block here is that some zones or contract offerers expect variable data. Variable data is data that is supplied by the caller that you don't necessarily know at the time the listing is created. A good example of this might be SIP7, which is a signed zone standard, so that you can have a server signature component to a listing. The signature, you have no idea what that signature is going to be when you create the order. So another type here is fixed data. Fixed data is data that you do know at the time that you're creating the listing. A good example of this would be, for instance, a conditional listing, where you can only fulfill this listing if you're also fulfilling this other listing, or maybe they're exclusive, so you can't fulfill this listing if this other listing has been fulfilled. For those, any fixed data has a hashing scheme based on the number of SIPs. You could have multiple SIPs that each require fixed data that are implemented on the same zone, and the zone hash parameter is where you encode that information. You basically, based on the version byte that's returned by the zone, it will either hash the fixed data array and compare that to the zone hash, or it will use one of these more complex encoding schemes. And as zones develop and more people are utilizing them, and if we want to explore different encoding schemes or more compact encoding schemes or what have you, then we'll add additional version bytes that you can support on the zone. Let's get into contract-based listings. This is another Seaport compatible contract. These are a brand new concept, and the idea is that you have a contract offerer. Standard Seaport listings, you create the listing, fill out all the parameters, the offer, the consideration, and then you sign it. And you validate. You call validate on chain. But that means that you are effectively committing to exactly what this listing is going to be upfront, and from the time that it begins to the time it expires. You could obviously set the price to ascend or descend on various items, but it gets tricky to do any kind of dynamic changes or calculations to the amount, and moreover, it's not really compatible with on-chain liquidity in a fully interoperable way. So what contract-based listings do is, instead of signing for a given listing, you, as the caller, you provide a contract order as one of the orders that you're fulfilling, and you bound what that order should be. You use the offer array to represent minimum received. If you're familiar with some of the the ways this works on Uniswap and things like that, is okay, since I am going to take the offer items on this listing I'm fulfilling, I need to receive back at least this many items in this amount. And then the consideration array, it represents maximum spent. Basically, since I'm going to be paying out the consideration items, this is the most I'm willing to give up. And then you also communicate arbitrary context, and this is all dependent on the SIPs that are being implemented on the contract offer. So you give all of you, and that's supplied as extra data. So we're reusing a lot of the same fields that you use on standard listings, but you're not signing those. You just supply them, and then Seaport will take those and hand them off to the contract offerer. The contract offerer then takes that information, can modify state, call other contracts, go grab tokens that it needs just in time from other on-chain sources or marketplaces or you name it, and then returns the offer and consideration arrays that it is comfortable with. So instead of validating via signature or ahead of time via a call, it's actually providing the listing that it's happy to offer just in time, right? And then Seaport takes that, treats it just like any other listing, can be matched, can be fulfilled as part of a batch and using fulfill available. And then once all of those executions have been completed, then Seaport will follow up post execution and call ratify order, which enables the contract offerer to clean up, modify state, so on and so forth. There's also a preview order function so that you can do a dry run, mainly meant to be called off-chain, like via ETH call or whatever, and see what the minimum received, maximum spent should be. It'll basically give you a benchmark, because you have to supply maximum spent if you're going to be spending anything. The contract offerer can actually, if they so choose, they can extend their offer. They can add additional received items or increase the amounts. So you can capture positive slippage that way. The contract offerer can elect to give you more than what you originally asked for, effectively. And indeed, you could even, if you trust the contract offerer, it's designed in a way where Seaport is going to enforce the original constraints you give it. You can see abridged logic here, where it's going to iterate through all of the minimum received items, the offer, and it checks to make sure that they're all present. But you could add more. And then on the maximum spent side, you have to supply anything that you're going to be spending, anything that's in the consideration array has to be explicitly provided. If you left that empty, then the contract offerer could not ask for anything in exchange. And that's basically a protection against interacting with malicious contract offers. And that's where preview order comes in handy. One other thing I'll point out here is if you take a look at the order hash, as there's no signature on contract orders, they're generated in time. The way that it works instead is that the order hash is mainly just used as an identifier. And it's a combination of the offerer's address, the contract offerer's address in the first 20 bytes, combined with the contract nonce. We track every single time that a contract order is fulfilled or skipped, we increment a nonce for that account. And so there's a distinct order hash for every fulfilled or skipped contract order. But it's not derived using the same hashing mechanics as a standard Seaport listing. Let's get into some optimizations. So the first thing I want to point out, by far the most significant optimization that's applied on Seaport 1.4 is the use of custom encoders and decoders. This is, you can see this library by Dylan Keller, who I believe is on the call here, called Ability, is a tool for generating these encoders and decoders based on a Solidity repo that you pointed at. And I'm just provided a sort of sample snippet here of some of the premises of this library. You can see this first one, we're encoding a bytes array at a given memory location and then moving it to a new memory location. One of the first things that these custom encoders and decoders do is, rather than inserting a lot of conditionals into the code base, which is the default in Solidity to protect against offsets, lengths, and in general out of range parameters, instead we simply mask those parameters. So it cuts down on overhead significantly. It does also deviate from the default behavior that you would see in Solidity. Our sort of position is that that deviation is something that we can live with. If you are trying to overflow a memory buffer or doing surgery on the offsets and lengths and all of that, that if you trip unexpected behavior, then it's kind of on you at that stage. But that's one of the big things. The next big thing, if you look at this decoder, the decoders, they read from call data, they read from return data, etc. You'll see there's a call data copy. Call data copy is almost never actually used by default Solidity, and that is there's a couple of reasons for that. One is that you can inadvertently copy over dirty upper bits. Another is just that most of the logic around decoding is pretty tightly scoped to the specific types. And Seaport makes heavy use of structs and arrays of structs and arrays of structs that themselves have arrays of structs inside of them. And when you add up all of that decoding logic, it gets pretty inefficient. And so by writing our own custom decoding logic, we're able to copy entire segments of the underlying structs and iterate over these arrays effectively. And the main sharp edge case to watch out for is the dirty upper bits that can be introduced. Luckily, as soon as you actually utilize any of these variables, the upper bits, for instance, if you're using a dirty address to perform a call to a target, those upper bits are ignored. If you actually pass those arguments through to a function or utilize them in higher level Solidity, the dirty upper bits are then checked and cleaned. But we don't need to be checking them repeatedly and redundantly. particularly once they've already been checked. So this definitely requires some care. I would not advocate that you just blindly hurl these custom encoders and decoders at your code base without careful weighing of the pros and cons. But for cases where you have really complex encoding and decoding schemes, it makes a ton of sense. There's some other cool tricks related to this same thing. If you look here, we do a lot of typecasting throughout the code base. This is an example of typecasting functions themselves. And the way that this is then implemented, if you look at this is an example function right at the entry point of the contract. And you'll notice that the order is not actually named, right? We have this custom name tag comment. That's because Solidity, by default, if you name an argument, it will use the default encoder to pull it into memory as soon as it's needed. Or even in call data, it's still hanging around. And it sort of preps that parameter to be read and validates all kinds of properties about what you're about to use. So instead, we directly decode this in place, typecast it to the correct types, and even utilize specific call data offsets for the correct location. Other optimizations that are pretty interesting, that are less all-encompassing, but are still kind of fun. Fulfill basic order, which is one of our hop paths. If you want to just do a simple listing, you can call this fulfill basic method. It's a bit of a misnomer because it's not actually simpler. If you want to simply fulfill a listing, you just call fulfill order. But fulfill basic order, you can pass in a subset if you assume certain things about the listing, like, oh, there's a single NFT that's being bought or sold, and everything else shares the same item type, right? It's like all the fees are paid out in Ether or WETH or what have you. And so fulfill basic order is really heavily optimized for that specific use case. We pushed it even further by mining a function selector with a 0-byte function selector. So it's at the very top of the function dispatch and cost less call data. That's fulfill basic order efficient 6GL6YC. And another interesting optimization and quality of life improvement is we, by default, if there are any excess offer item amounts on any of the orders that you're currently fulfilling, which will only happen in cases where you're using the order combiner functions, which is fulfill available and match orders, and you're supplying fulfillments that can aggregate transfers. If you have any leftover items on the offer side, then they're all passed along to a designated recipient. This is actually the only high-level interface, like breaking change, is that match advanced orders now takes a recipient. Fulfill available advanced orders already took a recipient. That was the de facto recipient of all of the offer items. Match orders and fulfill available orders all default to the caller as the recipient, or on the advanced cases, you can also supply the null address to default default to the caller as the recipient. But in the match case, it's going to ensure that all of the consideration items have been explicitly met. They all have to be paired against given offer items. But then if you have leftover amounts or unspent offer items, they're all sent to the recipient. And if there are offer items that you don't want, then you have to work around that by providing a consideration item, which can be a tip. You can always just tack it on to any existing listing, with the items and the amounts being equivalent and the recipient being equal to the offerer. Anytime that you have a source and target that are exactly the same, basically an execution where no transfer has to occur because it's a transfer to self, that execution just drop out and will be filtered. So you don't have to accept all of the offer items, but you have to explicitly reject rather than explicitly include them all. So this reduces a foot gun and is also a potential optimization, as you can cut down on call data quite a bit by not explicitly, you don't have to supply single fulfillments for offer items, particularly on fulfill available, when they can't be aggregated with other items or when it doesn't save appreciable gas to do so. That's basically it. I've shared here the link to our Seaport working group Discord. I imagine that a number of you are already here, and if so, it's good to see you. If not, I encourage you to come join us. And this is where we're discussing ongoing efforts to improve our test suites around the protocol, to develop new Seaport improvement proposals. If you are creating new zones, new contract offerers, and you want to see other marketplaces support those, including potentially OpenSea, then creating a Seaport improvement proposal is the perfect place to start. And it's still very early stages on that front, but I'm really excited to see where it goes from here. And more generally, just to stay up to date on everything that's happening with Seaport, I encourage you to come check it out. Thank you very much, and let's get into Q&A. Great question. So the Seaport trajectory, we first performed an informal security review of the initial version with OpenZeppelin. We then followed up with a formal audit with Trail of Bits. Then we kicked off at least at the time, the largest Code Arena competition ever, the $1 million prize pool. And then after the Code Arena competition for the first iteration found 2 high and 2 medium severity issues, we kicked off an audit with Spearbit. Now, everyone that's on this call is obviously familiar with Spearbit, and so I don't want to beat a dead horse fact here, but they are the best. Hari, Axic, Gerard, I see Michael on the call, Salman is all just incredible auditors and developers. So they cleaned up, they mopped up the first Code Arena competition, and then immediately launched into a follow-on review where they ensured that all of the fixes were adequately applied and that everything was ready to go. And so then we launched Seaport 1.1 on the heels of that, and it has been performing really well in production, at times being the top used contract on mainnet, deployed across many different chains, and has moved over 10 million NFTs in its tenure thus far. We were coming out of a pretty bumpy situation with the Wyvern protocol that OpenSea was using prior to Seaport. For those that are not familiar, there was a vulnerability in the Wyvern protocol, and patching that, we were able to successfully upgrade the protocol to patch the vulnerability, but it was very tricky to do so because of the governance delays to make that happen. And the protocol was also just structurally very dangerous. The way that you had a single user proxy that one malicious signature even could completely take over your proxy. It could delegate call out to malicious implementations and take ownership of this, and you got into a totally irrecoverable state. So we were really, really excited to get off of Wyvern and develop a secure and efficient protocol. But it also dictated some of our thinking around it, given that Seaport had a lot of new mental models and all of that. We purposefully restricted much of the functionality, including making all the external zone calls stateless, not including any notion of contract-based listings. And as more and more people started to build on Seaport and extend it and play with it and become familiar with the mental models there, it became clear that the protocol was time to open it up, extend its capabilities, and build on that foundation of a more simple and conservative implementation. So we then engaged Spearbit once we were ready with the initial set of features for this new version of Seaport. And that was a really fun, and I think the right way to approach it. My first piece of advice, and this is sort of a ontological statement, but before you're going into an audit, make sure you're ready for the audit. Make sure that you have all the test coverage, all the comments, all the documentation. Luckily, we already had a lot of that in place from earlier engagements and work, as this was an incremental version bump, and a lot of functionality remained the same. But that way, the auditors can really get in and focus on finding vulnerabilities and not just trying to make sense of your code. The Seaport code base is already tricky enough to make sense of in the guts of it. That engagement with Spearbit was a lot of fun because we were able to just focus on the guts of the new features, and specifically the encoding and decoding logic. I wouldn't have trusted anyone with that to really give it the attention and care that it deserved. And Spearbit also was instrumental in providing additional help with optimizations, which was really, really cool to see. So this second go around, what we learned was when you head into a code arena competition, if you want to do an independent audit as well, it's a good idea to do that up front so that you're not just inundated with I think on the version 1.0 that we had audited for Code Arena, we had like 13 distinct submissions for there was an issue with partial fulfillment where you could overflow the due to typecasting down to a UNT 120. So we got a lot of submissions there. Maybe it was because it was also $1 million prize pool, and this latest version was much smaller. But I also think it's because we had Spearbit really giving it a good comb through. The biggest learning experience from this go round is that if you don't very clearly specify the invariants that are important to uphold, then even auditors or code arena competitions can can miss things. And it's no fault to the auditors if they don't know what matters. And we had not been clear enough. There was an implicit invariant that, oh, we're moving the zone check to the end of executions. It should only occur after all the executions have completed so that any external protocols can utilize zones to perform their own accounting. And after realizing, once we had deployed 1.2, prior to going live on it, there were no marketplaces using it yet, but playing around with it in the Seaport working group, Andrew Lloyd discovered an issue where you could, in certain cases when you're using a conduit, you could transfer tokens after the zone check had been performed. So this was the key learning. Once we discovered that, we rushed out a fix to that issue, and in doing so, introduced other issues. There was a problem where post 1.2 fix, the zones on skipped orders, if you call fulfill available, Seaport will check, has this order that you're trying to fulfill been fulfilled already, or has it been partially fulfilled and there's not enough to fulfill what you need? Has it been canceled? Has it expired, or is it not in range in terms of time? If any of those things, or if it's a contract-based listing, did the call to generate the order revert? Any of those things happen, then the order gets skipped and marked as unavailable, and is filtered from all of the listings you're trying to fulfill. This is a very useful feature if you're trying to sweep the floor and buy 10 NFTs at once. You don't want a single NFT being purchased to cause the entire batch to fail. And you also can specify, I want to fulfill up to 5 of these 10, and only fulfill a certain number of them. So after applying this fix, turned out that we were still calling zones that were unavailable. Their underlying listings were unavailable, and just providing them with bunk data, with effectively garbage, because the listing had never been adequately processed because it was skipped. Then, after fixing that, and assuming that was the root of the problem, there was another even harder to find thing, which is the bug that we were talking about earlier, related to if you have excess offer item amounts, that you report the incorrect amount. All of this is downstream from a rushed fix. And what it really emphasized to us is, one, you never rush out a fix, especially if it's not a really critical issue. Obviously, if there are funds at risk and you can see it and it's like, well, we might introduce a problem, but the problem we're facing at this exact moment, it necessitates taking quick action, then you do what you've got to do. But you get in the war room and work through it. But if the issue is not a critical, hair on fire, funds at risk thing, we've learned to be deliberate, to take our time, and to use that as a indication that there are gaps in our test coverage. The key gap in our test coverage that we have identified as a result of this process is an over-reliance on individual test cases. So we have an entire 100% code coverage on our hard hat test suite, and our Foundry test suite is also, it fills in the gaps where hard hat can't cover inline assembly, so we have 100% coverage of all of the inline assembly. But code coverage alone can be a superficial metric, because while we're testing each feature in depth individually, we're not testing adequately combinations of features. There are many different routes. For instance, you could have a whole bundle of listings that you're all fulfilling at once. Some of them are skipped, some of them are restricted, some of them are aggregating different tokens. Some of the tokens are the executions are going to be filtered. How does that all come into play, and are there any dangerous assumptions or expectations that are violated when you combine them? So the takeaway is that we are currently looking into ways to, either through really aggressive fuzzing campaigns or through brute force combinatorial logic, to test as many or all of the different combinations of routes that combine all of these various features and conditions as to what types of listings and items and all of those conditions into our test as possible, which would have caught many of the problems that we're seeing, where it's really only when you are looking at multiple features at once that you will catch some of these edge cases. Thank you for having me. Thank you everyone for joining.